So in chapter 2, you read all about motion along a straight line. So there's a couple things we need to define with regards to motion, some terminology. We're going to be talking about something called mechanics. Mechanics, this should make you think of the word mechanical, so how things actually work. And in particular, we're going to look at how motion works. This field is something called kinematics. And we couple this mechanics with a field called dynamics, which we will study later on in the semester. These dynamics are going to be things that are called forces. These will be coming soon. So in kinematics, what we have are three quantities of interest. We want to know about position, and position is going to be something we call x. It's going to describe where something is. When picking x, because that's usually the standard, and it's referring to a frame of reference. So we need to draw a reference frame, and that will commonly be a coordinate system. So that's going to be a line here, a little line going horizontally, and these should be familiar. We're talking about an x and a y axis. So x is going to be a horizontal axis, y is typically going to be a vertical axis, and this is my coordinate system. And what we're talking about here is motion in only one direction along a straight line. So maybe motion back and forth along the x-axis. Other quantities we can describe for kinematics. We also have something called velocity, which we'll talk about in just a moment. Velocity, which we label with a v, and we have acceleration. Acceleration is labeled with an a. So these are three quantities of interest. Already we've taken care of position. We know what position is. It describes where something is in some reference frame. So position, we can circle and call that one done. Where something is in our reference frame is our position. And one of the big things we want to keep in mind for when we're talking about position and motion in general is we're going to be talking about translational motion of this little speck right here. And if this little speck, if we remember from chapter 1, that is the ideal particle or point particle. To understand velocity, a good starting point is to first get a grasp on what average speed is. Average speed describes how fast you're going. It describes the total distance you travel, so how far you go, divided by the total time it takes you to travel that distance. It doesn't care about anything that happens in between. Let's say you're making a trip and you stop on the trip. Let's say you backtrack. Let's say you get stuck in a traffic jam as you're driving along. None of this stuff, this stop, this backtrack, this traffic will be accounted for in your average speed. Average speed doesn't care about anything except for the distance you go and the time that it takes you. We usually do this in reference to Earth, in Earth's reference frame of Earth. Referenced to Earth. And to figure out more about this, make sure that you understand it. I suggest you try Checkup Exercise 2.1. So now that we understand speed is how far you go divided by how long it takes you, we can move on to velocity. Velocity, we describe it with a v. I'll put this little bar over it. That little bar denotes that I'm talking about an average. So little bar means average, and the velocity is going to be equal to x2, some position, divided minus x1, some other position, divided by the time it took you to get to the second position, minus the time it took you to get to the first position. So another way that we're going to write this is going to be v, a little bar over it, is equal to this delta x, the Greek letter delta means a change in x, divided by change in t. Now we're going to ask what are the units. Remember that little bracket right there means I'm asking about the units of v. So the units of position, in the SI system, a position is measured in a length, so that's going to be meters, and the SI unit of time is going to be seconds. So the units of velocity are going to be meters divided by seconds. There are a couple different ways that we can describe velocities. We can describe them with graphs, and we can describe them with straight up equations, with math. First, we'll start with our graphs. Here I have a graph. I've graphed position versus time. And we'll want to make sure we do this in every single graph we make. You have to label your axes. So you can see I've labeled position with x, and I've labeled time with t. And a very essential aspect of any graph you make in a science class, you have to put the units on. X is measured in meters. You notice I put the meters. T is measured in seconds. So I put the seconds. And what I've graphed here is a position versus a time for 3 points, point A, point B, and point C. So I know at a time of 0 seconds, whatever I'm talking about starts at a position that's 1 meter away from whatever my origin is. So I'm 1 meter away. 2 seconds later, I'm at point B. At point B, how far am I from my origin? I can trace my position over. I'm 4 meters away from my origin. Then I trace my path at point C. At 4 seconds after I start taking data, I can see that I am at 1 meter. Okay, so this is describing the position of a particle at any given time. Position of a particle at any given time. Position of a particle at any given time. And what I'm asked to find is the average between points A and point B. So I need to know the average velocity between A and B. Graphically, what would this be? Well, I can think about the units that I need for velocity. Remember, what are the units of velocity? Units of velocity are equal to meters divided by seconds. How can I get a meter divided by a second from this graph where I have a meter versus a second? Well, I can divide the numbers. If I divide on this graph, that's going to be the slope. So the slope on a graph of x versus t, position versus time, is going to be equal to velocity. Slope on a position time graph will give you velocity. So I need to find the slope between points A and point B. To find the slope, I take 2 points. This is a straight line, so I can take 2 points and find the slope. I need to do the y-axis versus the x-axis. In this case, it's a little confusing possibly, but the y-axis in this case is x, is position. The x-axis is time. To find the slope, I need the change in y over the change in x, or in this case, it's the change in x divided by the change in t. Remember, x is the y-axis, the up and down axis. T is the horizontal axis. So I have the vertical divided by the vertical axis divided by the horizontal axis. So change in x over change in t, which means I need x at point B minus x at point A. I'm figuring out the slope, the y position at the end minus the y position at the beginning, divided by the time at the end minus the time at the beginning. I can look at my graph, I can read my numbers straight off of my graph. What is my position at point B? Where am I at point B? I look at point B. What is my x position? My x position is 4. So I can plug in my 4. What is my x position at point A? My x position at point A is 1. So I can plug in my 1. 4 minus 1. My times, what are my times at these positions? My time at point B, I look at point B, trace it down to my time is 2 seconds. Minus my time at point A. Where's my point A? Here's my point A. What's my time at point A? My time is 0 because I'm at the origin. Okay, so 4 minus 1 is 3 divided by 2. And my units for this are going to be meters per second, the slope. So my velocity between A and B is 3 over 2 meters per second, 3 halves. Let me do the same thing for between points B and point C. Point B to point C, what is the slope of this line? Again, I'm going to read my values. I'm going to do change in x over change in t. This gives me my slope, my vertical over my horizontal. I do x at C minus x at B. Again, because I'm finishing up at point C and I'm starting at point B. I divide these two, divide xc minus xb by tc minus time at B. I can plug in my numbers. My position at C, x position at C, I am at 1. I can see that if I go to my C, trace it over to where I am on my y-axis, I am at the position x equal to 1. Minus x at B. X at B, if I remember from before, is 4, or I can see it straight on this graph. What is my x position? What is my position? I'm at 4. And then I divide by the time at C. The time at C, here's my point C, traced down to my x-axis, and my time at C is 4. So I plug in my 4 minus time at B. Here I am at B. My time at B is 2. 1 minus 4 is negative 3. 4 minus 2 is 2 meters per second. And I have my answer, my average velocity between B and C. And the important thing to note here, this sign, this negative sign, I can expect that graphically because this slope is going down, so it's a negative slope. So I have a negative velocity. Here between A and between B, my slope is going up, so I have a positive velocity, as I would expect. So I can test if I'm getting the right signs for my answers by looking at my slopes. A positive slope is a positive velocity, a negative slope is a negative velocity. And that sign, that negative or the implied positive here, is very, very important. So that sign that you get, a positive or a negative, is very, very important. Velocity can be positive or it can be negative. And that sign tells you the direction that you're going. So the velocity tells you how fast you're going and the direction you're moving in, which makes it something called a vector. Speed is different. Speed is always going to be positive. No direction is given for your speed. Speed does not care what direction you're going in, so it is something called a scalar. That's the difference between speed and velocity. So that was average velocities that we were working with. Recall there was a little line over them, meaning average. We also need to talk about something called instantaneous velocity. This is a little more useful, this is a little more practical, what people actually end up using. And the instantaneous velocity is the velocity at a very specific time. We can figure out this graphically, we can figure out this mathematically. Mathematically, we're going to need to use calculus. Graphically, we can use the concepts of calculus. So graphically, to figure out the instantaneous velocity, we look at the slope on the line between two vanishingly small distances from a point of interest. So what does that mean? Here I have a graph. I have a position on the y-axis plotted versus a time. And it's going to be meters over seconds. So the slope anywhere on this graph is going to give me velocity. If I look at the slope, let's say I want to know the instantaneous velocity right at this point. What I need to do is figure out the slope between two vanishingly small points, vanishingly small distance away from the origin. So I could try to figure out the instantaneous velocity by taking the slope on this graph from, let's say, this point and this point. Here I'm on the right side of my point. Here I'm on the left side of my point. I can draw in my slope. And is this going to give me a very good instantaneous velocity for this point right here? I don't think so, because it's not very close to it. So it's going to give me a completely different slope between these 2 points, other than the slope that is on that actual curve at that point. So I need to pick 2 points that are closer. I need to get closer and closer to that point of interest. So now I can draw this slope, and you can see my distance away from these 2 points, my distance away from this central point is getting smaller and smaller. I'm moving my line to get closer and closer to this one single point of interest. I'm getting closer and closer, and becoming my 2 endpoints to calculate my slope are becoming vanishingly small distances from that point of interest. And eventually, as I keep shrinking this down, this slope will get closer and closer to the instant velocity. The velocity at that one single point. Now, graphically, it's very difficult to do this. This is why we have the benefit of calculus. So mathematically, we have a definition for velocity. Velocity is equal to the limit as delta t goes to 0 of delta x over delta t. This is exactly what I was describing on the graph. Here's my point of interest, and I want to keep taking lines that get my delta t, where this is, here's my delta t, here's my x-axis, my t1 and my t2. As I decrease the distance between those 2 points, as I decrease my t1 and my t2, my slope gets closer and closer to that size, to describing that exact point. So I'm shrinking the line, shrinking my endpoints, making my delta t closer and closer to 0. And as I get closer and closer to 0, I get close to this point. And we should recognize what this is. In the calculus terms, in mathematical terms, the limit as delta t goes to 0 of a change in x over a change in t has a very specific calculus definition, v equal to dx over dt. And we will definitely want to keep this in mind. D. What is D? D stands for derivative. So the velocity is the derivative of x. If you remember what x physically is a position. So velocity is derivative of position divided by t. So if you remember derivatives, v is derivative of position. With respect to something, you always have to take a derivative with respect to a certain variable, and for velocity, it's the derivative of position with respect to t, which is time. So let's see an example. Let's say I'm given an equation for my position. So x of t is equal to 2.376 t squared minus 0.42 t cubed. And I'm asked to find what is the velocity of this particle at a time t equals 1 second. Well, to find velocity, v at some time, at any time that I'm interested in, is going to be equal to dx over dt. So I need to take the derivative of this. To take the derivative, I use the product rule. I bring my 2 down front. Product rule, bring my variable down to the front. I'm going to multiply by what I still have left, 2.376. I'm going to take t and raise it to the 2, the second power. I brought that 2 down to the front. 2 came down front. So now I subtract 1 from that exponent. This is a process. It's a process you should be familiar with called the product rule. And then I'm going to subtract. So there's our first part. And I'm going to subtract the derivative of the second part of my equation. I'm going to bring my 3 out front. 3 times my 0.042 times t to the 3 minus 1. Again, to get from here to here, it's just 2 applications of the product rule from calculus. Now I can write this all out. I can multiply my things together, so I get v of t, which is equal to the first derivative, the derivative of position with respect to time, is going to be equal to 4.752 times t minus 0.126 times t squared. From here to here is just pure algebra, which we should definitely all be able to do. If you're confused, I suggest that you try checkup 2.3. And read the math help section here. It's about differential calculus. If you do not understand that math help section, this is why you're watching these lectures 2 days beforehand. You need to send questions. If you do not understand this calculus, this math, how to take derivatives, send questions. So now we have a pretty good handle on velocity. Next quantity of interest is going to be acceleration. With acceleration, again, the direction matters. I would suggest looking closely at page 39 and 40 to see how to figure out direction. Direction for acceleration is going to refer to speeding up or slowing down. So not only does the difference in your speed matter, but the direction that that difference in speed is going will matter, and that will determine your direction. So you can read all about that on page 39 and 40. Acceleration, we have average acceleration v2 minus v1 over t2 minus t1, but we're working with calculus, calculus-based physics, so acceleration is going to be the limit as delta t goes to 0 of delta v over delta t. Or in other words, acceleration is equal to dv dt. Change in velocity over change in time. So this is going to be our definition of acceleration. There's another way we can define it. We can do derivative with respect to time of velocity, but velocity is just dx dt. So when we have derivatives written this way, this certainly means that velocity, that acceleration is the second derivative of x with respect to time. So there are 2 ways we can find acceleration. Acceleration can be the derivative velocity with respect to time, or it can be the second derivative of the position with respect to time. Both are equivalent. Both will give you acceleration. So acceleration, the time rate of change of velocity with respect to time. A lot of the problems that we're going to work are going to work with constant A motion, constant acceleration. This doesn't mean that acceleration is 0, it just means acceleration is a specific number. And if we have constantly accelerating motion, we have 3 very useful equations. First, velocity at some final time is going to be equal to velocity at some initial time plus a times the change in time. I'm going to alter these a little bit from what you see in your book. In your book, your equation looks like this. I'm going to tack this little f on here, and I'm going to put in a delta for the time. There's a couple of reasons I do this. This kind of really specifies that this velocity, this first velocity, is a final velocity. And it's going to be equal to whatever you start out with, your initial velocity, the initial speed you have, plus your acceleration times however long you're accelerating for. Your acceleration is going to change your velocity. So that is reflected in this equation. And I include this delta so that you don't confuse t with a plus sign. Okay. Second equation that we can use for constant accelerating motion is x minus x0. x0 is the initial position, is equal to 1/2 times v0 plus v times t. And again, you might see me changing things a little bit. I might have an xf. I might explicitly put in these final velocity and final position and a delta t. But they're the same equations. Number 3, we have x minus x initial, or x naught, is equal to v naught times change in time plus 1/2 a times a change in time squared. Again, I usually put in an f for the final position, and I like to put in delta t's so that I don't confuse it with the plus sign. And the final kinematic equation we'll want to know is going to be a times x minus x0 is equal to 1/2 times v squared minus v initial v naught squared. And we'll tack on my finals. Okay, these 4 equations are going to be tremendously useful for many of the problems you're going to solve. You are going to have to use a particular method of looking at what you know, what you don't know, and pick which equation to use. Occasionally you'll be able to use different ones. You'll be able to use multiple equations. The only way you're going to learn this is with practice, which is what you will be doing during the typical lecture time. Okay, let's test some consistency for all these equations that we've figured out. I'm going to solve this equation for x. So I'm going to say x is equal to x0 plus v0 delta t plus 1/2 a delta t squared. It's just one of my kinematic equations, and all I've done is add the x naught to both sides, plus x0 plus x0, to get this final result. Now I'm going to start taking derivatives. I take derivative of x with respect to t. So this should give me a velocity equation. Velocity is dx dt. I have some equations for velocity. Let's see if I can get one of them to come out. Derivative of x with respect to t. So what's the derivative of x0 with respect to t? I see no t's in this variable. There are no t's here. So as far as the derivative is concerned, this is just a constant. This is just a number. The derivative of a number is 0. Buckus goes away. Derivative of v0 times t. v0 delta t. I can think of this as the product rule. I can put a little 1 up here. And then we do the product rule. So I bring my 1 down front. I have 1 times v0 times delta t, and I take my exponent and subtract 1 from it. So delta t time to the 1 minus 1 power. Okay, and then I have 1/2 a delta t squared. I'm going to bring my exponent down in front. So I have 2 times my 1/2 times my a times my delta t. And I have my squared, and I need to subtract off 1 from the exponent due to the product rule. So this gives me v is equal to, I'm going to do dx dt, which is equal to 0, plus v naught delta t to the 1 minus 1. That's delta t to the 0. So that delta t to the 0 goes away and gives you 1, plus 2 times 1/2. The 2's cancel, and I end with 1. A delta t 2 minus 1 is going to give me an exponent of 1. So v is equal to v naught plus a times delta t. I got this just from taking a derivative of this very first equation I have up here. And this one, if you look back at your kinematic equations, is one of the kinematic equations we have already found. So now I know V is equal to V naught plus a times delta t. Well, if I want to know acceleration, acceleration is equal to dv dt. So I take the derivative of this with respect to time. v0, what's the derivative of v0 with respect to t? I see no t's in this entire variable, not multiplying by any t's, so that is a 0. As far as my derivative is concerned, v0 is constant, plus. There, my delta t, I'll explicitly put in my exponent of 1. I bring my exponent down front. 1 times a times delta t to the 1 minus 1. So a equals dv dt, derivative of velocity with respect to time. 0 I'm not going to worry about. 1 times a gives me a times delta t to the 0. Any variable raised to an exponent of 0 is equal to 1. So I get my final result. A is equal to a. Check mark, everything is self-consistent. Physics actually works. Two more things to talk about. First, we'll talk about a common example of constant acceleration motion, something called freefall. This is the example of something falling on Earth's surface. Falling on Earth. Earth has something called a gravitational pull. We're all familiar with Earth's gravitational pull. It's why things fall when you drop them. Earth pulls things down so that they reach a certain acceleration. The acceleration of an object falling on Earth's surface, we actually give it a special letter. The acceleration of falling on Earth's surface is equal to g, which has a value of around 9.8 meters per second squared. So that's how fast something accelerates when you drop it. It accelerates at 9.8 meters per second squared, and this is a constant value. There is one thing to note about the direction of freefall. Direction of freefall. Typically we have our coordinate axis, so I'll draw my coordinates in here. We have an x-axis, we have a y-axis. If I'm dropping something, what direction am I going in? I'm going up and down. I'm not going left and right. So the direction for the acceleration is usually in the y direction. We can use all of our equations, same as before, except we'll be moving in the y direction. And we need to pick a direction to be positive. Usually I find the easiest directions, the ones that make sense for me, is up seems positive, and to the right to me seems positive. So when I do problems, I assume anything that's going up is positive, anything that's going to the right is positive. In the case of a freefall problem, g is actually going down. Something is being pulled to the earth. It's accelerating as it falls. So g, in my choice, if I say up is positive, that means down has to be negative. So g is going to have a negative value. So if I write all my kinematic equations for this case, for freefall, and I'm going to assume that down is negative, then my equations look a little bit different. I have v is equal to v0 minus g delta t. Still acceleration is g, and the negative comes from the fact that Earth is pulling it down. The acceleration is positive, is in the negative direction. And I chose here up is positive, down is negative. I have y minus y naught is equal to 1/2 times v naught plus v times delta t. I have y minus y naught is equal to v naught delta t minus 1/2 gt squared. Again, the negative comes from my acceleration being down. And then finally, negative g times y minus y naught is equal to 1/2 times v squared minus v naught squared. And final point to make, to really drive this home, this is negative. These g's are negative. Negative g. Because I chose to say anything up is positive and anything down is negative. Way back over here with my coordinate axis definition. The final point I'd like to make regarding this chapter is a quick terminology note about a concept called terminal velocity that your book introduces at this point. This is when air friction balances acceleration and you fall at a constant velocity. So where does this happen? What's a good example of this? Let's say I'm a skydiver. So here's my little skydiver. And what does a skydiver do? He crazily jumps out of a plane and starts falling. So here's my little skydiver. He's inside of his plane. Here's a little door, and he jumps out. Jumps out and starts falling. So here's my skydiver sideways view. And this skydiver, he's a little bit crazy, so he doesn't pull his parachute, and he's just going to start falling. He's going to be falling at some specific acceleration. The acceleration he feels is free fall. The only thing acting on him is the acceleration due to gravity, is the gravitational pull of Earth. So he's going to accelerate with some acceleration that's going to be equal to g. And he's going to keep speeding up. He's going to keep going faster and faster and faster, until at some point he's going to feel air pushing against him. You can feel this if you stick your hand out the window when you're driving in your car and you feel air pushing against you. So eventually there's going to be a point when the amount of air that pushes on him, that pushes him up, is going to be equal and opposite to the acceleration due to gravity. At this point, he's not going to be accelerating anymore, and he's going to be traveling with a constant v. At this point, he has reached his terminal velocity, the point where acceleration cannot increase anymore due to air resistance or air friction. And that is the concept of terminal velocity.